As another application of double integral, consider the electric component capacitor and consider the parallel plate capacitor. That means it is built of two thin conductive plates separated with some uniform gap filled with some insulator, some dielectric. And we want to find the capacitance and the property of such a device. So it consists of two plates. First, consider just one single conductive plate, and this plate is charged with some electrical charge, and we want to find the potential and the intensity of the electric field near this charged plane. Let me repeat a few terms from physics. The Coulomb law says that if we have two charges, Q1 and Q2, then they attract or repel each other with this force, which is 1 over 4 pi epsilon. Epsilon is the permittivity of the space between the two charges, and r is the distance. If we take the force and divide by the charge, then we get the intensity of the electric field just described by the source of the electric field, Q1, the charge. If we take the force and we integrate in space, then we get the energy, the work that we must do if we remove or displace some charged particle in this electric field. And integrating 1 over r squared gives minus 1 over r, and the constants remain. If we divide this energy again by the Q2, the charge of the test particle, then we get the potential phi, which describes the electric field alone. And if we take the difference of the potential at 2 points, then we get the voltage between these 2 points. So first, let's consider one infinite plane that is charged with some constant charge density. Let's call the density sigma, and this will be the ratio of some charge delta Q divided by some area delta A. And we assume the charge density sigma to be constant in this infinite plate. You see, infinite plate is now easier to consider than a finite size plate. So consider the plate like that. We position the plate in the xy plane and consider a point here that is in distance z from the plane. And we want to find the value of the electric field at this point. Then consider some element of the plane, delta A or dA, and if this is positive, then the force goes this way. And for each element here, we can find a corresponding element on the other side that gives this vector field, this vector, and the sum of these two will be equivalent to just considering the direction of the vector of the electric field intensity in the vertical direction, because the component here will be annihilated by the component from the element on the other side. So the total intensity will be a double integral over the whole plane R2, and then each element dx dy contributes with a force like that, with the intensity like that, 1 over 4 pi epsilon. Now Q is the product of the charge density times dx dy, which is the element of the of the surface divided by r square, which is this distance from the point that is the source of the field to the point where we measure the field. But then we must multiply by cosine of this angle to consider the vertical component only. And cosine of this angle is equal to cosine of this angle, and this is equal to z over r. Where r is the distance of this element from the origin, and in the xy plane, r is the square root of x squared plus y squared, where x and y are Cartesian coordinates of the small piece of the plate that we consider now as a source of the electric field. So this is an example of a double integral, and this is the application for the capacitor, because we will need the intensity of the electric field. How to evaluate this integral? Well, for pi, epsilon, sigma are constants, so we can write it in front of the integral. And r is square root of x squared plus y squared. And sorry. That's not correct. R is the distance from the source of the field to the point where we measure, and in the xy plane, no. We should write it with a different letter, say rho. Rho is here. So sorry, cosine of this angle. Yeah, this is still z divided by r. So this is correct. But r is square root of z squared plus rho squared. So this is equal to square root of z squared plus, and rho squared is x squared plus y squared. Okay, let's write it again as an integral, and now z is a constant. This is the distance from the plate where we measure the intensity of the electric field. And here we have r cubed, which is z squared plus x squared plus y squared. Square root of that and cube, so to the power of 3/2 dx dy. Well, it looks like a difficult integral, but fortunately we will be able to compute this. But before we find the value, the result, before we integrate, we can come to one very interesting, important conclusion, even before we integrate, before we compute the integral. If z is in meters, x is in meters, y is in meters, then we have some cubic meters in the numerator. Meter square to the power of 3/2 cubic meters here. So this whole expression is some form of cubic meters divided by cubic meters, which is a dimensionless unit. And not just units, but also the values are sort of independent of something interesting. If we introduce a substitution, x is z times alpha and y is z times beta, for positive z is a constant. Z is a constant. This is the distance of the point where we measure the intensity. the distance from the plane. So z is the positive constant, and xy are the two independent variables of this function, and we integrate over x and y. If we introduce this transformation, that means from the old integrating variables xy, we come to the new integration variables alpha and beta, then we can rewrite this integral as some constant sigma over 4 pi epsilon. And then if z is a positive constant, then when x and y run from, entire R2, then so we'll do alpha and beta. This is just a sort of rescaling. But if we rescale the entire plane, we get again the entire plane. dx is z d alpha, dy is z d beta. So one z, another z, another z, z cubed. And if we write x is z alpha, then this bracket looks like z squared plus alpha squared z squared plus beta squared z squared. But we can factor out z squared, and we have 1 plus alpha squared plus beta squared. And when we take the exponent 3/2, then we have z cubed 1 plus alpha squared plus beta squared to the power of 3/2. Z cubed in the numerator, z cubed in the denominator. And now we can reduce z cubed, and this result, this integral, which describes the intensity of the electric field in the distance z from the plane, is independent of z. Yes, it's a surprise, but this is correct. So, you see, even before evaluating the integral, even in cases where this function would be too complicated to integrate, then just from this manipulation we see that this is independent of z. This alone would be a very important result of its own. But fortunately we can integrate this if we transform to polar coordinates. R cosine of phi, well, phi is used, alpha is used. Okay, let's go back to xy. And let's consider the following integral. And let's go to xy instead of alpha beta. And let's forget the constants for the moment. So we have 1 over 1 plus x squared plus y squared to the power of 3/2 dx dy. So if we introduce the polar coordinates, r cosine of alpha and r sine of alpha. This alpha is the angle, this has nothing to do with that alpha. Then, this is a function of r alone, and we can integrate over phi. This is a constant, and integrating phi from 0 to 2 pi gives 2 pi, and r runs from 0 to infinity. That means from origin to infinity. And if we have the function 1 over 1 plus r squared to the power of 3/2, and instead of dx dy, we write r d phi dr, and d phi is already integrated to 2 pi. Well, and now we can use substitution. 1 plus r squared, say some u, then 2r dr is du, and we have integral at 2 pi, integral when r is 0, u is 1, when r is infinity, u is infinity, and if we borrow this 2, then 2r dr is du, and here we have u to the power of 3/2, which is u to the power of minus 3/2, and when integrated, this is u to the power of minus 1/2. We divide by minus 1/2, that means we multiply by minus 2, from 1 to infinity. At infinity, it is 0. At 1, it is 1. So the result is 2 pi. So when we go back to our intensity, we see that the intensity at the point Z is sigma divided by 4 pi epsilon times this integral, which is indeed a constant, not depending on Z, equal to 2 pi. So we have sigma divided by 2 epsilon. Sigma is the density, the charge density of the charged plate. Epsilon is the permittivity of the media between the 2 plates. So that was the intensity from one plate, and if we have a capacitor consisting of 2 plates with equal charge, one positive, one negative, then the total intensity is 2 times more, sigma divided by epsilon. Well, if this is the intensity of the electric field between the 2 plates, then the voltage is the intensity times the distance and the charge density is the charge divided by the area. And such a capacitor is described by the important parameter capacitance, and this is the charge divided by the voltage. And if we divide charge Q by the voltage U, we see that the capacitor is A epsilon divided by D. A is the area of the plate of the capacitor. Now we consider finite size capacitor. D is the distance of the plate, and epsilon is the permittivity of the insulator, of the electric in the gap. So that was the application of double integral to find the intensity of a charged plane.